The last topic we're going to discuss in Chapter 12 deals with allylic halogenation. So if I take an alkene and react it with bromine at very low concentrations in light, I can actually brominate that alkene at the allylic position. So you see that there are two allylic carbons present. And of course, if I brominate either one of them, I get the same product. I get this 3-bromo cyclohexene. Now, what's happening here is, as we have seen already, in the presence of light, bromine is going to dissociate homolytically and produce bromine radicals. And those bromine radicals then are going to react with this alkene. Now, we've already seen that bromine radicals abstract hydrogens from alkanes. And the question is, what's going to happen when a bromine radical reacts with an alkene? If we're looking at this particular example, we can see that there are three different types of hydrogens. So the first hydrogen is a vinylic hydrogen, right? The second hydrogen is an allylic hydrogen. And the third hydrogen is simply a normal methylene hydrogen. And we can look at the energetics of the radical that forms when these hydrogens, any one of these hydrogens, is abstracted. So let's take a look at that. The first one we'll look at is abstracting the vinylic hydrogen. So when I remove a vinylic hydrogen with bromine, I get HBr, and then I get the vinylic radical, right? So vinylic hydrogen with HBr. Now, I can also abstract the allylic hydrogen, and the result is I get an allylic free radical. And lastly, I can abstract the simple methylene hydrogen, and I get a secondary alkyl radical, right? Now, when I compare the energies of these three, why is it that the allylic radical is the only one extracted? So notice I don't get any of the bromination at the vinylic carbon, and I don't get bromination at the methylene carbon. It only occurs at the allylic carbon. And why is that? Well, if we take a look at these structures and we think about what stabilizes radicals, which we've talked about quite a number of times this chapter, hopefully you could guess by now it is resonance, right? So resonance is the key. Now, so what happens is bromine abstracts that allylic hydrogen, right? And so we form this allylic free radical. So here I have my allylic free radical, and now that allylic free radical I can draw a resonance structure of, right, where it donates to create a double bond, right, with one of the pi electrons of my alkene. And the other pi electron goes to that upper carbon. And so the result is another allylic radical. So these two allylic radicals, they're identical in energy, and so they're going to be in resonance with one another, delocalizing that radical one electron. So now it's going to, I can react that with bromine, and I can create a carbon-bromine bond. And of course, homolytic cleavage of that bromine bond places that one last electron on the second bromine, and I generate my product, right? So the 3-bromo cyclohexene plus a bromine radical. And of course, that bromine radical then can abstract another allylic hydrogen, and my chain propagation continues. Now notice we've only talked about bromination, and the reason for this is because, again, as we saw a difference in the regioselectivity between chlorine and bromine, this also applies to allylic halogenation, where we don't see the selectivity with chlorine. For example, if I take cyclohexene, again react it with chlorine now, low concentrations in the presence of light, I do get chlorination at the allylic carbon, but I also get chlorination at the methylene carbon, right? And you know, when we look at the product distribution, it's a fairly significant amount of chlorination at that methylene carbon. And so, in terms of synthetic use, it's okay, but it's not very selective. So another key component of this reaction deals with concentration. Notice I've stressed bromine at low concentrations. And the reason for this is simple. So if I'm going to take you back to the second semester, and we have already seen this reaction of an alkene with bromine. Now, obviously, we didn't have light present. There's a good reason for this, but we know that at high concentrations, so a 1-to-1 mole ratio of alkene to bromine, we get electrophilic addition. Right? So bromine adds across the double bond, and I get a vicinal dibromide. Now, how can I avoid that? Well, we use a reagent called N-bromosuccinimide, or we can abbreviate that NBS, in the presence of trace amounts of HBr, and this provides very low concentrations of bromine. And the way that it does this, and this is the structure of NBS, right? So succinimide is simply this structure without the bromine, so a hydrogen is in its place. So this is called N-bromosuccinimide. And so N-bromosuccinimide will react with HBr. And what happens is you produce succinimide plus bromine. So notice I can produce, this reaction is producing bromine very slowly. And so now once that bromine forms in the presence of light, it can dissociate into bromine radicals. And now that bromine radical can react with an allylic hydrogen, right, which we've already seen, to produce the allylic radical, and that allylic radical then can react with the small concentrations of bromine that are present, and we can get our product being formed, right? And of course, we're regenerating bromine, and that reaction is going to propagate itself. So let's look at a couple of reactions. The first reaction here is simply 1-butene. So 1-butene will react with NBS, and when we're looking at trying to figure out the products of these reactions, we simply have to look for allylic carbon. So with 1-butene, we see that there's only one allylic carbon, and so NBS is going to brominate that allylic carbon, and the product is this, right? So I get 3-bromo-1-butene. Now, what happens if I have a little bit more complicated alkene, right? So let's look at something that looks like this. One thing that I want to point out is the reagents. So notice the reagents, I just write down NBS and light. And I did say that I need trace amounts of HBr. There certainly are present, trace amounts of HBr are present in this reaction, and typically we don't show them as reagents. All right, so here I have an alkene. What do I have to do? I have to look for allylic carbons. How many allylic carbons do I have in this reaction? Well, I have an allylic carbon here, here, and here, right? So I have 3 allylic carbons. And what I do is I say, well, all right, what type of allylic carbons do I have? Because I know there is some regioselectivity for bromination. The one on the left is a secondary allylic. The one on the top right is also a secondary allylic, but the one on the bottom is a tertiary allylic. And so we see that tertiary allylic carbons are going to have their hydrogen abstracted at a much higher rate than secondary, and therefore we get essentially one product, bromination at that tertiary allylic position.